Mastering function ranges, a vital component of the Cambridge IGCSE Additional Mathematics syllabus. You will learn how to identify the set of all possible output values, or y values, for various function types, including linear, quadratic, modulus, and transcendental functions. Understanding ranges is essential not only for sketching graphs, but also for determining if an inverse function exists, a common requirement in your exams. We will focus on the specific algebraic techniques and graphical interpretations that will help you secure those top marks. We begin with linear functions of the form f of x equals mx plus c. For the IGCSE syllabus, the domain is often restricted to an interval from a to b because linear functions are strictly monotonic, meaning they are always increasing or always decreasing. The range is simply the interval between the y values at the two endpoints of the domain. To find the range, you just need to calculate the function value at each end of your domain and write the resulting inequality for f of x. Let's look at the function f of x equals 3x minus 2, where the domain is restricted to x between 1 and 4 inclusive. First, we substitute the lower bound of the domain, f of 1. Next, we substitute the upper bound, f of 4 equals 10. Since the function is increasing, our range is simply all y values from 1 to 10. On the graph, you can see the domain on the x-axis corresponds exactly to this vertical interval on the y-axis. Next, we move to quadratic functions. F of x equals ax squared plus bx plus c. Unlike linear functions, quadratics change direction, so the range depends heavily on the vertex. The first step is often to complete the square to find the vertex coordinates, h and k. This tells us the maximum or minimum point of the curve. If the coefficient a is positive, the parabola opens upwards, making k the minimum value. If a is negative, it opens downwards, making k the maximum value. Crucially, if the domain is restricted, you must check if the vertex falls within that domain. If it does, it will be one of your boundaries. Let us find the range for f of x equals 2x squared minus 8x plus 5 for all real values of x. First, we factor out the 2 from the x terms. Now, we complete the square inside the bracket. Half of negative 4 is negative 2, and we subtract its square, which is 4. Distributing the 2 gives us our vertex form. The vertex is at 2, negative 3. Since the coefficient of x squared is positive 2, the graph is a U-shape. The lowest possible value is the y-coordinate of the vertex. Therefore, the range is f of x is greater than or equal to negative 3. The modulus function, written as f of x equals the absolute value of g of x, always outputs non-negative values. This means the range is naturally bounded. To find the range, it is often best to sketch the graph of y equals g of x and reflect any part that lies below the x-axis upwards. For a function of the form f of x equals the absolute value of ax plus b plus k, the vertex is located at x equals negative b over a. The minimum value is k. For a standard linear modulus function shifted vertically by k, the vertex occurs where the expression inside the modulus is 0. The range will then be all values greater than or equal to k, provided there are no other reflections or domain restrictions. Consider the function f of x equals the modulus of 2x minus 6, then minus 1, for all real x. First, we find the vertex by setting the inside of the modulus to 0. The vertex occurs at x equals 3. Substituting this back in, we get the minimum value, which is negative 1. Since the modulus part, the absolute value of 2x minus 6, is always greater than or equal to 0, the smallest f of x can ever be is 0 minus 1. Thus, our range is f of x is greater than or equal to negative 1. We can verify this algebraically. If y equals the modulus minus 1, then y plus 1 equals the modulus. Since a modulus is always at least 0, y plus 1 must be at least 0, meaning y is at least negative 1. Now we turn to transcendental functions. Exponential and logarithmic functions have ranges that are strictly defined by their asymptotes. The general form of an exponential function is e to the power of kx plus c. An exponential function never reaches its horizontal asymptote. If the leading coefficient a is positive, the function stays above the asymptote. Conversely, if a is negative, the function stays below it. Logarithmic functions, however, behave quite differently. Unless the domain is restricted, a logarithmic function can output any real number. While its growth slows down, it continues to positive infinity as x increases and plunges to negative infinity as x approaches the vertical asymptote. Let's find the range for the exponential function f of x equals 5 minus e to the power of 2x. We know that e raised to any power is always positive. Therefore, the term e to the 2x is always greater than 0. If we rearrange to make the exponential the subject, we see that 5 minus y must be greater than 0. This mathematically proves that y must be less than 5. As x gets very large and negative, e to the 2x approaches 0, so f of x approaches 5. As x gets large and positive, the function goes toward negative infinity. The range is f of x is less than 5. Note that it cannot equal 5, as the exponential never reaches 0. Today we are looking at the range of trigonometric functions. Trigonometric ranges for sine and cosine are determined by their amplitude and vertical shift. These functions are periodic and wave-like, oscillating between a fixed maximum and minimum. For functions of the form f of x equals a sine bx plus c, or cosine bx plus c, the maximum value is c plus the absolute value of a, and the minimum value is c minus the absolute value of it. The value c represents the equilibrium or midline of the wave, and the absolute value of a is the amplitude, which is how far the wave travels above and below that midline. Now for the tangent function f of x equals a tangent bx plus c, the range is simply all real numbers because the graph has vertical asymptotes and extends infinitely in both vertical directions. When working with squared trigonometric functions, like sine squared, remember that the values are restricted between 0 and 1 before you apply any other transformations. Calculate the range for f of x equals 4 cos of 2x minus 1 for x between 0 and pi. Over the interval 0 to pi, the cosine function completes a full cycle and covers all values from -1 to +1. To find the maximum y value, we replace the cosine term with its maximum, which is 1. This gives us 3. To find the minimum y value, we replace the cosine term with its minimum, which is -1. This gives us -5. The midline is at -1, and the wave goes 4 units up to 3 and 4 units down to -5. The range is therefore the set of all values between -5 and 3 inclusive. Let's look at the concept of rational functions. For rational functions of the form f of x equals a over x minus b plus c, the range is restricted by a horizontal asymptote. As x becomes extremely large or extremely small, the fraction part of the function approaches 0. This means the function value gets closer and closer to c, but never actually reaches it. A more advanced but highly effective method for finding the range of rational functions is to use the inverse. The range of a function is identical to the domain of its inverse. By finding the inverse function and identifying its excluded x values, we can definitively state the excluded y values of the original function. Example: let's find the range of f of x equals 3 over x minus 2 plus 4. To find the inverse, we swap x and y. Now, solve for y. First, subtract 4. Rearrange the equation to isolate the term with y. We get y equals 3 over x minus 4 plus 2. This is our inverse function. We now look for the domain of this inverse. We see that x cannot be 4, because that would make the denominator 0. Since the domain of the inverse is all real numbers except 4, the range of our original function is all real numbers except 4. This matches our horizontal asymptote at y equals 4. Let's solve a typical Cambridge IGCSE past paper style question. The function f is defined by f of x equals 5 minus the modulus of 2x plus 3 for the domain where x is between -4 and 0 inclusive. Find the range of f. For modulus functions with a restricted domain, we must check the vertex and the endpoints. First, the vertex, we set the inside of the modulus to 0. Since -1.5 is within our domain, we calculate the y value at this point. F of -1.5 equals 5 minus 0, which is 5. This is a potential maximum because the modulus is being subtracted. Now we check the endpoints of the domain. For x equals -4. For x equals 0, comparing our values, the highest y is 5 and the lowest y is 0. The range of f is the set of values from 0 to 5 inclusive. Let's review common pitfalls to ensure you don't lose marks on your exam. The most common mistake is only checking the endpoints of a domain. For quadratic or modulus functions, if the vertex is inside the domain, it will always be either the maximum or minimum value. Notice how in our previous example, the value at the vertex gave us our upper bound of 5. For exponential and rational functions, remember that the function approaches the asymptote, but never touches it. For f of x equals e to the power of x plus 2, the range is strictly f of x is greater than 2, not greater than or equal to 2. Always double-check your variables. Domain refers to x values inputs, while range refers to y values or f of x outputs. In your final answer, ensure you write f of x or y rather than x. When finding the range of sine squared x, many students mistakenly think it's -1 to 1. However, squaring a negative makes it positive, so the range of sine squared is actually 0 to 1. To achieve top marks in your additional mathematics exam, keep these strategies in mind. Whenever you are asked for a range, a quick sketch can prevent major errors. Even a rough drawing of a parabola or a modulus V-shape will immediately show you if you should be looking for a maximum or a minimum. Use the inverse function shortcut. If you are struggling to find the range of a complex rational or algebraic function, try finding its inverse first. The range of the original function is exactly the same as the domain of the inverse. Finding where an inverse is undefined is often much simpler than analyzing the original curve. Watch for inclusive versus exclusive. Pay close attention to the brackets or inequality signs in the domain. If the domain is x is greater than 0, then your range calculation at 0 must also be exclusive. If the question uses less than or equal to, ensure your range reflects that with the correct notation. Check for restricted domains in trig. Don't just assume sine oscillates between -1 and 1. If the domain is restricted, say from 0 to 90 degrees, the function might only cover a portion of its usual range. Always check the values at the boundaries. It is time to test your understanding. Please pause the video and attempt these 3 practice questions. Take your time with each one, ensuring you consider asymptotes and vertices where necessary. We will go through the solutions shortly. Let us look at the solutions. For the linear function, we substitute the domain boundaries. F of -2 is -7, and f of 3 is 18. For the quadratic, we complete the square to find the vertex. The vertex is at 3, 1. Since the coefficient of x squared is positive, the minimum is 1. For the exponential, at x equals 0, f of x is 1. As x tends to infinity, the exponential term tends to 0, so f of x approaches 4.